A marble in a bowl. A uniform marble rolls down a symmetrical bowl, starting from rest at the top of the left side. The top of each side is a distance h above the bottom of the bowl. The left half of the bowl is rough enough to cause the marble to roll without slipping, but the right half has no friction because it is coated with oil. Part A. How far up the smooth side will the marble go, measured vertically from the bottom? Part B. How high would the marble go if both sides were as rough as the left side? Part C. How do you account for the fact that the marble goes higher with friction on the right side than without friction? Okay, so here is our bowl. We have friction on the left side, mu is positive, there's no friction on the right side, and we start with a zero velocity at the beginning, and then we roll without slipping. That means the contact velocity is zero, all the way to the bottom, a distance h from the top, and then we have a frictionless surface on which we have a contact velocity v center of mass minus omega final angular speed times r. So this part has no friction. And at the end, when we reach the top, we're going to have zero center of mass translational velocity. So all there will be remaining is minus omega final times r, capital R, for the contact velocity. So we want to start with the uniform sphere moment of inertia, because the marble is a uniform spherical shape. So it's going to be basically the moment of inertia of a sphere we have to consider. Now, when you concentrate on a sphere, you can see that we have the polar angle theta, azimuthal angle phi with respect to the x-axis, polar angle theta with respect to the z-axis. And if we look at a radial distance r from the origin, we have dr basically is our is one side of this parallel shaped, parallel piped, and we're going to have r sine theta, that's the component of r on the xy plane, r sine theta d phi as one of the sides, and then we will have r d theta, that's the arc length, that's the remaining side. So we will have r d theta, dr, and r sine theta d phi as defining the volume element of a sphere. So we can see that the volume dv in a spherical surface is basically r sine theta d phi r d theta dr. Okay. And if we have a uniform mass distribution, the mass density rho will be equal to the total mass, capital M, divided by the volume of the sphere, 4/3 pi capital R cube. So this will give us 3m divided by 4 pi r cube for the mass density. Now, for rotations about the center of mass, we can calculate the moment of inertia, I center of mass. This will be the integral. Now, the integral over theta will be from 0 to pi. The phi will be 0 to 2 pi, so we will be basically going over all possible angles phi here. And then if we go from 0 to capital R, we will have basically spanned the whole volume. As you can see, theta goes from 0 to pi. That's enough, because then we will get a slice here, and this slice will be rotating as phi goes from 0 to 2 pi and covering the full volume of the sphere. So we will have the theta integral from 0 to pi, the phi integral from 0 to 2 pi, and r integral from 0 to capital R. Now we're looking at a distance r sine theta from the rotation axis, so that's our distance for this volume element. Therefore, we will have r sine theta square rho dV. So rho dV is our mass element. So we can see that dm will be rho dV. So as you know, the I moment of inertia is integral r squared dm, where r is the distance from the rotation axis, and for this volume element, that distance from the rotation axis will be r sine theta. The rotation axis is the z-axis in this case. So this will be equal to the phi integral basically gives us a 2 pi, so let's evaluate that already here. So we will have the remaining integrals from 0 to pi, the theta integral from 0 to capital R, the r integral, r square sine square theta, and then we will have for dv r square sine theta dr d theta, and this will be multiplied with the mass density rho. So you can see that I have r here, so this makes r square sine theta d theta d phi dr, but I have evaluated the phi integral already. It gives me a factor of 2 pi. So the moment of inertia is going to be 2 pi times rho, which is 3m divided by 4 pi r cube. The r integral r to 4 dr gives me capital R to 5 divided by 5. And then I have the remaining theta integral from 0 to pi, a sine squared theta multiplied with sine theta d theta. That's going to give me sine cube theta d theta. So this will give us 3m r square. So we have an r cube here. This will make this r to 5 r square. And then we will have this 2 making this 4, 2. So we will be left with 3 capital M r square divided by 10. And then we can evaluate the integral sine cube theta d theta. It's going to be sine square theta is 1 minus cosine square theta. For sine cube theta, I'm going to substitute 1 minus cosine square theta sine theta. So this integral will become then integral from 0 to pi sine theta d theta minus the integral from 0 to pi cosine square theta sine theta d theta. Now this will give me 3 over 10 mr square. The integral of sine theta d theta is minus cosine theta, so I obtain minus cosine theta here. And the integral of cosine square theta sine theta d theta, if you call u as cosine theta, you will see that du is minus sine theta d theta. So we can substitute that here. This will become plus u squared du, so it's plus u cube over 3. So this will give us plus cosine cube theta divided by 3, because I have utilized the minus sign here as well. And all of this will be evaluated between angles 0 and pi. All right, so we can basically plug in the numbers here for theta. So I center of mass will be equal to three over 10 mr squared If I plug in pi here, I will get cosine pi equals minus 1. So that will give me minus 1. It's going to give me plus 1. Then if I put pi in cosine cube theta, that will give me minus 1 over 3. Minus 1 over 3. And then I can substitute zero, so that gives me minus 1, because it's minus cosine 0, and then I will have plus 1 over 3. So this will give me 3 over 10 mr squared. You can see I get 2 over 3 here, and I have minus 2 over 3 here. Minus minus becomes plus, so it will be 2 over 3 times 2. So that will give me 3 over 10 mr squared times 4 over 3. The 3's will cancel, and I will be left with 2 over 5 mr squared. So that's my result for the moment of inertia of a sphere for rotations about the center of mass axis. So that's basically this rotations about the z-axis. Now let's concentrate on what is happening at the top of the left side. So at the top of the left side, I have, if I draw the free body diagram of this spherical marble, I have the weight mg pointing down, and because it's going to be rolling without slipping, the friction will be a static friction, Fs, that will be pointing up. So if I look at the net force on the y-axis, the net force on the y-axis will be the static friction minus the weight of the marble. That will be equal to m times a, and a will turn out to be negative. It's going to be in minus j hat direction. So if I look at the net torque acting on this marble, it's going to be r cross f, so it's going to be minus r fs in k hat direction. So you can see that your fingers point towards the application point, and curl them towards Fs, you will see the thumb points into the page. So that's going to be equal to I center of mass times alpha, Newton's second law, rotational form. So we can see that the static friction will be equal to I center of mass times magnitude of alpha divided by r. We can put the absolute value here to make sure we're doing this right. It's going to be 2 over 5 mr squared alpha divided by r, and that will be equal to 2 over 5 m alpha r. Okay, and that will be equal to minus 2 over 5 ma. So if I keep that in mind, a is going to be negative. Otherwise, I can also take that into account and make this in minus ma j hat direction. Then a is going to be positive. A is the magnitude, and in that case I don't need this minus sign here, so this is going to be 2 over 5 ma. So a is equal to alpha r. We have rolling without slipping. Okay, so with that we can substitute 2 over 5 ma for static friction minus mg. The weight is equal to ma minus ma, and that will give us 7 over 5 ma is equal to minus m is plus mg, and that will give us acceleration is equal to minus 5g over 7 in j hat direction as a vector. Its magnitude is equal to 5g over 7, so let's keep this in mind. The system will accelerate, the marble will accelerate with this initial acceleration minus 5g over 7 in j hat direction. So that will be the acceleration of the ball. And if I look at the velocity of the center of mass, it will be 0 at the beginning, and then as time goes by, it will accelerate with this acceleration minus 5g over 7t j hat. So it's going to be accelerating downwards, so the velocity of the center of mass will be increasing in time, and angular speed of the center of mass will be v center of mass. Well, angular speed omega will be v center of mass divided by r, and that will be equal to 5g over 7r t. Okay, so the marble will start accelerating with this acceleration minus 5g over 7 in minus j hat direction, and then we will have an angular speed 5g over 7 rt, so it's going to increase its angular speed in time, and the velocity of the center of mass is increasing in time minus 5g over 7t j hat. Now let's concentrate on the bottom of the ball. At the bottom of the ball, we will have um, h, the distance that we had traveled minus h will be equal to minus 1 over 2 at squared, because we have acceleration in the downward direction, so that will give us a time 2h divided by a square root to reach the bottom. So we can calculate the final velocity of the center of mass at the bottom. It will be minus at, so it's going to be minus a square root 2h over a, so it will be equal to minus square root 2ha j hat. This is going to be our final speed when we substitute for t square root 2h over a. Omega final will be equal to v center of mass over r, so it's going to be square root 2ha divided by r. That's the magnitude of the final angular speed. And substituting for a 5g over 7, we can see that the final center of mass speed will be 10 gh over 7 square root, and final angular speed will be 1 over r square root 10 gh divided by 7. Okay. Now we can see that we have a final kinetic energy of the marble when we reach the bottom. Final kinetic energy equals 1 over 2 m v center of mass final square. That is our translational kinetic energy of the center of mass, and rotational kinetic energy 1/2 I center of mass omega final square. So this will give us 1 over 2 m. So v center of mass final we have found to be square root 2ha, so it's going to be 2ha plus 1 over 2 I center of mass we have found to be 2 over 5 mr square omega final square, which is 1 over r square 2ha. So it's going to be 1 over r square 2ha. That's omega final square. So we can get rid of these 2's here and these 2's here, and the r squares will cancel as well, and we will be left with mha plus 2mha over 5. So that will give us 7 over 5 mha. So acceleration was equal to 5g over 7, as you can see here. So if you substitute 5g over 7 here, you can see that this is going to be equal to mgh, which is the initial potential energy of the system as expected. Because the static friction does no work, we have the potential energy turning into kinetic energy. So we can note here in rolling without slipping, we have the velocity of the contact point Vc is equal to 0 if S does no work. Therefore, we have potential energy turning into kinetic energy. So if you look at what's happening on the right side of the hemispherical bowl, let's concentrate on the right side. We have initial kinetic energy we have found at the bottom of the bowl to be equal to mgh. We have a final kinetic energy, that's just the rotation because it's not going to be rising anymore, 1 over 2 I center of mass omega final square. Initial potential energy is 0 joules. The final potential energy will be equal to mgh prime. So what happens on the right hand side when we have no friction? So let's note that the contact point velocity Vc is going to become Vc is equal to the center of mass velocity minus omega final times r, where V center of mass will be decreasing as the marble goes up, as the marble climbs. It's going to be V center of mass is decreasing, so it's going to be a negative contact velocity, which is called a backward slip. So it's going to be a backward slip in this case. Now we have conservation of energy, delta U is equal to minus delta K on the right hand side because we have no friction. So we have conservation of energy with no friction. So our final potential energy minus initial potential energy, mgh prime, will be equal to our initial kinetic energy, mgh, minus the final kinetic energy, 1 over 2 over 5 mr square I center of mass omega final square, which is 10 gh over 7r square. So that's what we have found here for omega final. So this is going to give us a cancellation of these 2's here. The r squares will disappear as well, and this 5 will make this 10 2, and we will be left with mgh minus 2 over 7 mgh, which is 5 over 7 mgh, and therefore we will see that h prime will be equal to 5 over 7 h. So that's what we obtain from conservation of energy. The angular speed omega is not changing in time after we pass to the right hand side, but we do see that this velocity of the center of mass will decrease under the influence of gravitational acceleration. And what will happen at the top? We can see that at the top, when we reach this 5 over 7h, the velocity of the contact point will become minus omega final times r, and it's going to be a pure rotation. There won't be any translation of the center of mass. Okay. Now part B asks me, how high would the marble go if the both sides were as rough as the left side? Okay, so if I had both sides as rough, because the static friction does no work, H prime would be equal to H, since the work done by static friction is 0. So I would see that the kinetic energy that I have acquired at the bottom would be turning into a potential energy the same way it happened when it was falling on the left side. So there will be no energy loss, so H prime would be equal to H. And part C asks me, how do you account for the fact that the marble goes higher with friction on the right side than without friction? Okay, so let's see. So in the case of no friction, part of the energy remains as rotational kinetic energy. So therefore the height the marble climbs is less than the case with friction, because with friction at the end I have all of the kinetic energy turning into potential energy, so it's going to be there's an energy difference between the two scenarios, so I find that it's going to be H prime will be less without friction because I will have remaining energy as rotational kinetic energy due to the slipping of the marble. So that's going to be the final contact speed minus omega final times r. Okay, so let's summarize what we have done here. We have a uniform marble. A marble has the shape of a sphere. It rolls down a symmetrical ball. It starts from rest at the top of the left side, and it falls a distance h, rolling without slipping. The left half of the ball is rough enough to cause rolling without slipping, but the right side has no friction. So I want to know how far up the smooth side the marble will go, and how high would the marble go if the both sides were as rough as the left side, and how do we explain this result. So we have a rough left side, a smooth right side. We start with zero velocity, zero contact velocity to start with, and then we have a static friction here. So we can say that we have mu s is positive, So it's going to be rolling without slipping under the influence of the static friction because the contact velocity is zero, it's static friction. It's going to gain rotational kinetic energy and translational kinetic energy of the center of mass, and then with no friction on the right hand side we will be losing because there's gravitational acceleration, we will be losing the velocity of the center of mass, but the pure rotation will remain as we go up. So it's not going to go as high as h as we have found out. So this drawing actually is not quite right. So we can say that it actually goes to a height h prime here. And when we reach this height h prime, velocity of the contact point is minus omega final times r. So first I calculated the moment of inertia of a uniform sphere. A volume element of a sphere has r sine theta d phi, r d theta dr. As you can see in this geometry, we have the arc length r d theta, dr the radial incremental distance, and r sine theta d phi is basically this distance that we travel for the projection on the xy plane. The uniform mass density is capital M divided by 4/3 pi r cube. In order to calculate the moment of inertia, we have to look at the mass element whose mass is rho dv and find its distance to the rotation axis. The distance to the rotation axis, which is the z-axis, is r sine theta. So it's going to be integral r sine theta squared dm. And for dm, we substitute rho dv, and then we see that theta should go from 0 to pi. So we get this slice here, and then when we have phi going from 0 to 2 pi, this slice will go over the whole space when r travels from 0 to capital R as well. So this integral gives us 2/5 mr squared as the moment of inertia. On the left side, we have static friction pointing up, mg pointing down. So we have for the translational acceleration, static friction minus mg is equal to minus ma j hat. So acceleration will be downward. The net torque is minus rf s k hat equals I center of mass times alpha, that we find using the right hand rule. And we see that the static friction is 2/5 ma when we substitute it into the Newton's second law translational form. Acceleration is 5g/7, or vector, as a vector it's minus 5g/7 j hat. So the center of mass will be increasing in time. Speed will be 5g/7 t at time t. And angular speed omega will be v center of mass over r, 5g/7 rt. When do we reach the bottom? When h is equal to 1/2 at squared, when time is equal to square 2h/a. So that gives us our final angular speed, 1/r square root 10gh/7, and final center of mass velocity speed square root 10gh/7. And we see that if we write the kinetic energy of the marble at the bottom, the translational plus the rotational, we obtain 7/5 mha, which is equal to mgh as expected, because rolling without slipping, Fs static friction does no work. On the right side, we will have initial kinetic energy, this 7/5 mha, which is mgh. Final kinetic energy will be 1/2 I center of mass omega final square, purely rotation. And final potential energy mgh prime, initial 0. I see that the contact velocity becomes v center of mass minus omega final times r, and v center of mass decreases as the marble climbs, so it's going to become negative, which means it's a backward slip. Conservation of energy applies because I have no friction on the right hand side, and writing delta k is equal to minus delta u, we obtain h prime is 5/7 h. And at the top we have contact velocity, contact speed minus omega final times r, so pure rotation remains. If the both sides are as rough, then we would have H prime is equal to H, because the static friction does no work, it would be the same scenario. So this energy, final kinetic energy, would be turning into potential energy, again mgh. But in the case of no friction, because we have part of this energy remaining as the rotational kinetic energy of the marble, because we have basically no friction acting on the system, so the rotation remains. So we will have a part of the energy given to rotational kinetic energy. Therefore, the height that we reach in the case with no friction is less than the case with friction.